Hello. Hi, today we're going to talk about, okay. Okay. Okay, so we're talking about magnetism. You've all had magnets in your house, maybe you've had them stuck on your fridge and so on. You know that they attract each other and stuff like that. We're going to get into a little more detail, okay, to see some of the things, what makes a magnet, how they work and stuff like that, okay? So, magnetism. First of all, there are three types of materials that we refer to when we're talking about magnets, okay? There are permanent magnets. Those are the things you typically think of as a magnet. It's magnetic. They're really not always permanent forever, but that's what we call them, permanent magnets. Then there's stuff that is ferromagnetic, okay? So an example of that would be this paper clip, okay? The paper clip is attracted by magnets. So I have a magnet here, it gets stuck, and but it is not a magnet itself. So we call it ferromagnetic. It gets affected by magnets, but it's not really a permanent magnet. And the last thing is non-magnetic things, non-metals and such. Okay, so you really do need to know those words. Next thing, why is a material magnetic? There's a few things you need to know. First of all, in that material, they need one of three metals, okay? Iron, cobalt, and nickel. Okay, iron, cobalt, nickel. The other metals do not become magnetic, or at least not significantly. So aluminum on its own, you can try it. You're not going to make a magnet out of it. Iron, cobalt, nickel. The other thing, there are some lanthanides and rare earth metals that can become magnetic, but that's kind of a little bit not really a high school topic. So iron, cobalt, nickel. The second thing is the electrons. It turns out the electrons are spinning in those elements, in those atoms. Now, if they are spinning in random directions, you're not going to have a magnet. If they're spinning in the same way, then you can actually have a magnetic material. So let's look at that. And if we look at a piece of metal, and it has to have one of those three metals or more than one, and we look at a random piece of metal, chances are the spins, and I'm going to show those with arrows, are going to be going in random directions. So you're not going to have a magnet. By the way, each of those areas of metal where they actually are kind of a group going in the same direction, we call that a domain. Okay? You don't really need to know that for an exam, but it's interesting. So all these domains are spinning, the electrons are spinning in different directions. They're not lined up. You're not going to have a magnet. If they are spinning in the same direction, now I know we're talking about spinning electrons, and I'm just showing it with an arrow, but if they're spinning in the same direction, and they all line up, we are going to have a magnet. And we're going to end up with a north pole for the magnet and a south pole for the magnet, right? South at this end and north at that end. Okay? There's another really interesting consequence of this is if I take a magnet. Now, when I was a kid, I always knew there was a sort of north pole and a south pole, and I always wondered, well, I'd like to break one and just end up with the north pole and end up with the south pole, and then I could have fun with those. But it turns out you can't do that with magnets. And the reason is, imagine I take this magnet, and I take it and I snap it into two, okay? Let's say I use deflection to break it. And I snap it into two pieces, so now I end up with two magnets that are separate, okay? So this is one magnet, and this is another magnet, okay? Well, it turns out that I don't end up with just the North Pole. If you look at the alignment of the spins, these spins are still, this will be a new South Pole, and this will be a new North Pole. So when you break a magnet, as much fun as it would be, you can't break it into a separate North and South Pole. If you break it, you're going to end up with two smaller magnets, each with a North and a South Pole. Okay? So that helps explain that. So that's a good starter for magnets. We're going to start talking about magnetic field lines.